Okay, good. Maybe what we can do is just close the web cameras for some time. When I have a question to ask, I'll ask you to turn the web camera on. Maybe that will allow the connectivity to be better. All right, so let's do a quick recap of where we were yesterday, what we had done yesterday. We had taken a look at the Faraday's law. We've taken a look at Faraday's law, and we had seen that if I have a flux which is changing, I can create an induced EMF or electromotive force, which we'll call it V induced, which in the circuit is going to go as E dot dl and is given by the rate of change of the flux with time, or is minus n d by dt integral of t dot ds. So we had seen that there was a transformer EMF. Well, basically, V was a function of time. V varied with time, but the circuit was stationary. The circuit or the loop, that was stationary. We had taken a look at some of the examples with the circuit based on that. Today, what we are going to do is we are going to extend this quickly to motional EMF. We're going to see how we can calculate it. There are two different methods we can use to calculate it. But motional EMF, as you can see from the name itself, means that the circuit is moving in a constant B field, in a constant flux. Not constant flux, but constant B field. So the magnetic field does not change with time, but the circuit is moving. We're going to see how we can do the calculations with this motional EMF. And from there, we are going to then extend the Maxwell's equations. We're going to go back to Maxwell's time, and we're going to see what Maxwell thought of to be able to come up with these equations which we credit to him today. That would be the goal for the lecture today, and let's see what all we can cover. Let's start with the motional EMF, and there are two methods we can use to calculate motional EMF when the circuit is moving. Again, remember, V induced is minus d by dt. If there's some n number of turns, integral of v dot ds over the surface of that loop. In motional EMF, v is a constant, but the circuit is moving around, which can mean two things. One is that the circuit surface area is increasing or decreasing with time. So this is changing with time. The limits over which we have to do the integration are changing with time, or this dot product, which we have, this dot product could be changing with time. So either we could have the circuit expanding or contracting, in which case the surface area is going to change, and then the integral limits are going to change. Or what we may have is that the circuit is rotating about in the magnetic field, in which case the direction of E with respect to the direction of ds is going to change with time, and hence the dot product is going to change with time. These are the two basic cases we can have. We can calculate motional EMF directly by using this equation, directly by looking at that. Or we can calculate notional EMF due to this V induced by another equation, which is, let's say, if the circuit is moving with a velocity u in a magnetic field V, we can do this integral u cross B dot dl going from 2 to 1, going from a point 2 to point 1, u cross B dot dl. U is the velocity with which the circuit is moving. B is the magnetic field, and dl is the path you're going to take on the circuit.
Sir, sir.
Hello? Yes, yes, Jeff?
Sir, the audio is breaking, sir.
Okay. Okay, let me do one thing then. Can I just cancel this? I will call from the phone and then I will dial in again. Is it breaking a lot?
Yes, sir. Now it is clear, but sometimes it breaks, sir.
Okay. Uh, when it breaks, let me stop and then can we do one thing, please? Can we just turn the web camera off from your side?
Yes, the webcam is clear, sir.
No, can we turn the web camera off?
I can see your image, sir.
You can see the screen. But instead of that, can we turn the web camera off? Can you turn your web camera off? All right. Let's see if that helps. Otherwise, tomorrow I will start dialing in from my phone also. But for that, I need another headset, which I don't have today. Is this better now or no?
What do you think? Is it better? Now also you are not getting clear, sir.
Now, okay, just a second then. Let me figure out something. Just a second, please. Is this better now?
So noise is adding, sir. Echo. Noise is full, sir.
Is it better now? Is the voice better? Is the voice better now here?
It's not that much better, sir.
Hello?
Yes, sir. Can hear you.
Hi, Jay, can you?
Hello, Jay. Can you hear me now?
Yes, sir, I can able to hear.
Okay, let's do that. I'm calling it from the phone, but I'm going to be writing on the screen. Can you hear me well, and can you see my screen?
We can hear, sir.
All right, so what I had been saying was that the Gaussian EMF can be calculated by two methods. Either we can use this method over here, where we do the direct integral and we figure out how things in that integral, or what we can do is use another equation which is given by the motion, the velocity with which the circuit is moving, cross product with the magnetic field or magnetic flux density over which that circuit is moving to, and we integrate it over the complete part of the circuit. So either of these two equations will allow us to calculate the Gaussian EMF. Let's take an example and see what I mean by this particular. Again, let's take our R2 and we'll calculate the Gaussian EMF with both the methods. What I have is some rails. These are conducting rails here. And I have a bar which is moving on that by a certain velocity. If I make my computer circuit, it is calculating the Gaussian EMF at that place. That place as this bar is moving around. Let's assume that B is perpendicular, B is coming out of the board. So the B is uniform and is coming out of the board. Let's assume this is X direction, Y direction, and coming out of the board is my Z direction. Now if we notice the V induced, if I use, I have to go from point 2 here to point 1. I have to go through that path. And again, I am to assume that my DL path is this way. I have to walk along this circuit everywhere, and I have to assume my DL path is that way. So it is U dot DL. You go from what we call negative of your induced voltage to what we call the positive of your induced voltage. If I am using this induced voltage only happens for the moving part of the circuit. So what I have to integrate this part is the only place where I have to integrate this part is where the circuit is moving, which would, in this specific case, would be only in this region here. I have to just integrate it from 2' to 1'. Let's assume that this specific reference is height h. So I have to calculate V from 2' to 1. U cross D dot dl. I have to go from here to here, and I have to do that integral. That is only over the part of the circuit changing in time. U, as we have, is some magnitude of U in x direction. dl is a part I have from 2' to 1', so I can take a small element in this place here, which would be my dl. If I'm calling this to be y direction, dy in y direction, and my already d naught is direct. We can now start substituting into the equations, get V induced from y 0 to y is equal to h. I have to take small differential element that I've created in dl, start from this point and keep on moving. This whole line is integrated. That's what is defining the integral. U we said was some u in x cross d in z. I mean, we call it b dot. So u cross s dot z on dl, which we have said was in y direction. Now remember again, for cross products, whether you are in any coordinate system, just if you're in coordinate systems of Cartesian, you can go very simply circuit way that if x cross y will give me x, y cross z will give me x, z cross x will give me. So I arrange these in, and then I can go around in a counterclockwise fashion to get the answers like x cross y is equal y cross z is equal to x, z cross x equal to y. Similarly, if I am cylindrical coordinate system, we have the vector r, vector theta, vector z, or vector phi, vector z. And in that case, you have r cross phi would be z, phi cross z would be r, and similarly z cross r would be phi. If you are going in the direction, in the counterclockwise direction as this is laid out, you would get positive values. If you go in the clockwise direction, then you get negative values. For example, phi cross r would be minus z. And in spherical concepts, we have vector theta, we have vector phi, who's applied r cross theta would be phi, theta cross phi would be R, and so forth and so on. Remembering these rules allows take these cross products, either calculating of magnetic fields or calculating of your V induced in this case, having around playing with your left hand and trying to figure out what the rules are going to be. So if I go back to my example now, I have X cross Z. X cross Z is going in the clockwise direction, opposite of the counterclockwise direction. Z is going to be the dimension, which is Y, but because I'm going in the clockwise direction now, so V induced are going to be equal to 0 to X, 2 B dot constant, X cross Z is minus Y dot dy of Y, and thus it just becomes minus U B dot, Y dot Y is 1. I go from 0 to H of dy, and I get the answer minus U B dot H. What this is telling me, again, reminding you of discussion yesterday, this negative is telling me that the V induced is actually in the opposite what I had. In this calculation, we can V induced is negative on this terminal 2 and is positive on the terminal 1, so that if I have a load attached to that, the current in the load would start flowing this way, and that my circuit will continue to flow out of the direction. When we do all our final calculations, when I get a negative, this basically means that V induced is opposite what I starting with the big problem. Please always keep that in mind. Again, as mentioned, I just always go counterclockwise so that I don't have to think through the problem. I always go counterclockwise, and if my answer is, if the result is opposite of what I am thinking of, or not, result is opposite of my convention, I just end up getting a negative in front of the answer. Let's do the same problem now by doing the input and see if we can. I have my bar, which is moving with velocity. And what is happening that over time, as time is changing, this cross-section area which is being enclosed by the circuit is changing. As this bar is moving forward, let's say at time t is equal to 0, it was here. After some time, this bar has moved forward. And thus, here now, time equal to t, this area has changed. This area, so what I have to do, form if I was going to calculate with the integral form, I have to have V induced minus d by dt of b dot ds. Again, choose a specific direction. I said I can then shift to counterclockwise. So I'm going to assume that this is negative, this is positive. This is the dl which I have within my V induced. And my ds is going to be pointing upwards. So my ds is vector ds in z direction. V dot ds now just becomes z dot z and v dot ds. So my v induced is minus d by d. I have to integrate it over the surface area. D dot ds. Now you would notice is this area which I am integrating it over, this limit is a function of time. As my time, this limit is from 0 d. I have to define this limit with this which I have. Well, let's assume that at T naught, the width was some x naught. So at T is equal to T naught by surface area would be some x multiplied by h. At T is equal to T, this area would have it would be x naught plus u times h. I go to another part. This surface area starts to increase, and thus at time t, which is so at any specific trying to calculate my surface, my width is going to be x naught plus ut, and my total surface area is going to be x plus x divided by h. So that's basically where my limits are going. I can calculate my v induced as minus d by d. D1 is constant ds over the surface area. So it just becomes minus d by dt v dot of naught plus ut h, and then you do the differentiation. This part goes to this part here goes to 0. Only this part will exist. V dot h. So if you notice, that is exactly the same with u cross b. That's, but it should be the same, otherwise you have obviously made some errors. So the answer is always with which you can calculate your Boostable EMF. One is go and integral. The other is try to use u cross beta dl. So most of the problems doing the integral obviously makes your life a bit easier, because when I mix proportional and transformer EMF together, then you can just calculating it this way will give you both the answers. Will give you the answer due to the changing of B with time and changing of the surface area with time T2, or surface changing of flux circuit with time also. So both of these will give us the same answer. To illustrate that point, let's do another example. But before I do that, do you have any questions? Yeah? Yeah, do you have any questions? I will continue forward. Is my voice clear?
Yes, sir. Yeah, mic.
Fine. Let's continue forward then. Let's do one last example of Faraday's law, and with that we will finish Faraday's law. And in this example, both transformer and motional EMF. So the example is here. But let's think that the magnetic field is also changing in the turbine. I have a circuit. Let's call this X, Y, Z plane. I have a circuit which is aligned around the x-axis. Let's say it has an, and let's assume that V is in time along with circuit rotating around V. Let's assume that V is in Y direction. Such that it is V naught sine of omega. So I have a loop with some width W and height H. This loop is centered on the x-axis. And what this loop is also doing, as it is centered around the x-axis, the loop is rotating about the x-axis by the same angular velocity omega, or angular frequency omega. So there is a loop. Magnetic field B is in the Y direction. And that is also as sine omega t. And the loop in this magnetic field, the loop is centered on the x-axis. It is the x-axis and rotating about in that direction. So if I take a look at this loop, I have to now go surface area of the loop. Basically, what I have to be able to calculate is, ultimately I have to calculate V induced, which is minus N d by d of V dot ds. I am again going to counterclockwise, so I am assuming that the current is flowing this way, which means by this is positive, this is negative, thus I get V induced here. I'm still going to assume that. But now what I have to be able to, what is this doing? And if you notice, once my loop is rotating about the x-axis, this dot product changes with time too. It is perfectly vertical when V is the XZ plane, when V is, sorry, when the circuit is in the XZ plane, my surface normal is going to be plus Y. It changes, this surface normal keeps on changing. Let me just show it on my view. I'll just turn the video on for a second. And right, if you notice, this hat is the loop. This hat is the loop that's about it. Let's call this x-axis. This hat is rotating about around the x-axis. If I put my circuit model, my pointer this, which I'm holding is, that circuit model is out of the surface of the loop. And as time is changing, this circuit model a different angle, y-axis, as I'm going through. The surface model is changing around its direction. So not only is my changing in time, but what my B.ds, my B is flowing out, my B this direction, when my circuit is right here, my B and ds are in the same plane, I have the maximum value of B.ds. When my hand has moved around, my ds is now pointing downwards, but B is pointing is still in the same y direction. My B.ds now is low. So B.ds is going to be different. So not only is my value of B changing, but this surface normal, because the surface normal keeps on taking different angles, but surface normal, the dot product with B and ds also keeps on changing with time. So I need to be able to account for that. All right. Next, how we can go about solving that problem. So I have to now have a surface of the vector some angle here. There is a vector which is and I should say this is making an alpha with the y-axis. At any time t, this is making an angle alpha with y-axis. That is used at time t is equal to 0. At time t is equal to 0, alpha is equal to alpha. Then at another time t, this angle by omega. By ds is ds in the normal direction. By B.ds becomes y, or ds is normal direction of it, and y dot normal would be y product which I have. So that would y dot normal would be cos of the angle which it makes, or cos of alpha plus omega t. If I calculate my phi, that is over the surface area of the circuit. I can start putting the values in. B is B dot. B dot ds we have already calculated. Sorry, B is also changing with time, so I should call it sine of omega t. So B is sine of omega t. B dot sine of omega t. Alpha plus omega ds. All these are integral of ds. ds is basically which I have to do for the surface area which is enclosed within this shaded part over here. All these terms are, this integral just becomes b naught sine of omega t cos alpha plus omega t integral of ds. But the surface area which I have, integral of ds would be nothing but this shaded surface area which I have, which would be the width multiplied by the height h. So this just becomes b naught sine of omega t cos alpha plus omega t with times h. Let me just put this w separately with times h. That becomes my n. My v induced is minus d minus n d phi n by dt. And if I now look at it, it's minus n d by dt of v dot h w sine of omega t alpha plus omega t. If I just use the chain law for the integral, I will get minus n d dot h w. Then I integrate sine omega t first. I get cos alpha plus omega t omega cos of omega t. And then I get d dot w. Now I integrate that. There before I get sine omega t, that is constant, that is the same. Just so when I do that, I get omega minus sine of alpha omega t. So you can write this as d dot h omega hw omega cos of alpha plus omega t cos omega t plus n b dot h w omega sine omega t sine alpha omega t. If you notice now, first term, this term over here is coming by sine is varying with time. This is because he is varying with time. The first term I get is because this omega t is varying with time. That's the differentiation which I did. This term is your transformer EMF. And the second term which I get is because alpha plus omega t is changing with time because my loop is moving with time. And that's the second portional part by EMF. My total EMF is given by the sum of the transformer EMF plus the motional EMF, but the way we do this math, both these terms will be going up, and you can easily differentiate which was coming from transformer EMF side and which was from the EMF side. Those are the examples I wanted to do with Faraday's and the calculation with Faraday's law. What I will do is I'll send here some questions for you to practice on. I will send them tomorrow morning my time, so tonight your time, and we can probably give you a few days for you to practice those questions on, see whether you have understood, and do those questions in your tutorials. See whether you have understood and whether you can now apply what we have talked about in the last 1.5 lectures to solve the problems with Faraday's law. Any questions do you have on Faraday's law? Any questions you have there? Alright, let's continue and let's summarize all you have done the course, and let's figure out Maxwell now. What Maxwell is. So far what we have learned in all the course is we have the Gauss law, which is del dot B is equal to rho, and rho is the charge which you put in the system, which is your Gauss law for electromagnetic, which is your Gauss law for electrostatics. Then you have also looked at E is equal to 0, which is something which you probably have been doing from your childhood, since you break it in parts. L dot B is equal to 0 is just a statement of that, which is Gauss law of magnetism. And then you del cross H is equal to J, which is your basically saying that what you create and the magnetic field has to magnetic field has to be closing around the source. It has to curl around the source. That's what we had learned there. And over the last lecture and a half, we have learned the last equation, which is del cross E is equal to minus del V by del, which is Faraday's law. What you would notice, all these are they are not right from first, at least when they were discovered or when they were written in their form, they were completely coming out of. It's only later with mathematics that you can derive these laws from very first basic principles, but at the time they were discovered from 1866 to about mid-1890s, these were purely experimental laws. And one thing you notice here is that there is an asymmetry in the 4 equations I have written, and asymmetry specifically in these 2 equations. Faraday's law says, think B with changing magnetic field with and E field. As you change the magnetic field, create an electric field. But as these experimental laws are written right here, there is no effect of changing electric field. There was Maxwell. These experiments had been done. Del dot E is equal to 0 was famous experiments run by Coulomb, and then Gauss converted started to convert form. Coulomb basically said, if I take a spherical charge, he took a spherical ball of metal, he made a ball of metal, and then when he went inside that ball, he found that he could not feel any forces inside that ball. And that led to Gauss law. Okay? Something which we know from our childhood. If you take a magnet, you break it up, you still have a north pole and a south pole on the magnet. Del cross H is equal to J started with Oswald. Oswald was doing experiments with wires carrying currents, and he found that if he brings two wires which are carrying currents close to each other, they would attract, or in the direction of the current, and they would repel. However, if the wires were not 90 degrees, then there was no force. So Oswald was doing those experiments, and Ampere's law came right out of those experiments. And Faraday's law came with the which Faraday did. Basically, you take a magnet, you pass it over something which is considered to be non-magnetic or very weakly magnetic, you can start attracting it. You take that magnet and you pass over a conductor, the magnetic field. If you just pass the magnet over a conductor fast, you start creating a current. And here was Maxwell sitting here, and then we looked at these, seems to be an asymmetry in physics. There is something we are missing, which the experiments have not picked up. And this is the thought process we went through. Let's consider this Del cross H is equal to J. Let's consider the law. Whether this law is fully complete law or not. If I take the law, Del cross H, this is your Ampere's law, which basically is saying, if I have a source of current, I create H with around J. If I have a source of current curls around the magnetic field. Plus, if I take divergence of this, divergence. It basically is if I L dot Del cross H is Del dot J. Remember? This is a curling field. H is a field. If a field is turning around it cannot diverge out. Or chasing its own way. It will have to be going around in a circle. It cannot run outwards. Either it can run outwards like the electric field, or when it is chasing its tail, it can only run around it. So this divergence of a curling field has to be zero. If a field is, if I take the divergence, it cannot be flowing outwards at the same time. So the divergence of the curling field has to be zero, and then you get an equation which is del dot J is equal to 0. And this is a totally wrong equation. This equation basically states that you cannot have any source of current ever. Any electrons or remove any electrons or have any kind of a current source ever. You have another equation which you may have seen in your semiconductor physics, and that is a charge quantity equation, which is del dot J is equal to minus del rho by del T. Which basically says, if I go to a point, at that point I'm able to add charge which is varying with time, I would create a place around that time, around that place. This is basically your KCL, Kirchhoff's voltage law. This is what to calculate your charges and your current which is going to flow in a semiconductor, in a MOSFET kind of a circuit, or any other material. This is another universal law which we go off. And Maxwell is here in this equation. That is this, if del cross H is true, then get into trouble because it is going to be telling me equal to 0 that there cannot be any divergence of current. But I cannot have a current source, which we view is not possible. So Maxwell said that this equation here is incomplete. But this equation doesn't tell us about the whole nature of the electric and magnetic fields. So there is something missing in this equation. Let's find out what is that equation. Well, we have dot D is equal to rho. If I take derivative of that, again remember this is derivative with space, this is derivative with time. I can interchange that. I can write del dot D is equal to, del dot del D by del T equal to del rho by del T. I want my charge quantity equation, del dot J is equal to del rho by del T. It's telling me my charge should ultimately turn out to be minus del dot T by del T. If I take Ampere's law, I have H is equal to, this is the experimental part, to the part which Ampere actually discovered. This is the part related to this law, del dot T by del T, called displacement current. This is the experimental part. This is the experimental part. Addition of this del D by del T is pure maths. It's coming purely from Max's point of view. Basically, Maxwell realizing that del cross H is equal to J does not tell me about the universe completely, because otherwise I get into trouble with another universal law, which is the charge continuity equation. Now let's see what happens if it diverges. The left hand side is going to be del dot J del dot del D by del T, or del dot J is equal to minus del D by del T. We know del D by del rho by del T. So this is minus del rho del T. Just computing this part over here. And now I get the charge continuity equation back. This is Maxwell's solution. This is his genius. And this is the only reason why Maxwell's equations are called Maxwell's equations. Let's again take a look at the Maxwell's equations as they stand today. In the differential form, there is L dot E is equal to rho, and E charge, put in the system. L dot B is equal to 0. L cross H is equal to J plus del D by del T. And del cross E is minus del B by del T. Out of these, everything except for this is an experimental law. Displacement current was purely coming out of maths. Displacement current was only identified, only verified in World War II when we started building radar systems. It's only when we went to higher frequency terms we could actually measure a term which we introduced as displacement current. So this was almost 80 years, not 80, but 75 years, roughly 75 years after Maxwell discovered this. This law these equations which we see today, and we named them after that, were actually finalized these were finalized by Ross in 1890s. Equations, the form which we are forms which are covered. If you look at the original, this concept was introduced by Maxwell in 1866. It was a very seminal paper written in 1866. If you look at Maxwell's paper, a mathematician, but a really poor mathematician. He was a really good thought scientist, but as a mathematician, Maxwell was not that good. If you look at the equations in 1866, those equations have mathematical errors in them. However, because he was the one who was able to identify changing magnetic field, then have an effect on magnetic. Nature loves symmetry. So that symmetry should be present in nature. And he went about for where can I find that? And he was the one who that is what as will be seen there, as we will see later on, and as further. Because of that contribution, because of the contribution of del D by del T, we still give credit to that. That's why equations. All right. take a look at these equations. Let me just if we take a look at what all these equations lead us to. There are 4 field terms in equation. There is E, E, B, but they are not independent terms, they are related by material properties. Remembering again, E is absolute E in any material. Is the permittivity absolute multiplied by the electric field E, or in terms of relative permittivity, it is absolute E. B, mu H, which is mu naught, R, H. Absolute, so there are 2 material properties. Absolute being your property of the material, how strongly does the material polarize when I apply an electric field. Mu being the ability of magnet. How strong can I make it into a magnet when I apply a magnetic field externally to that material? So there is 2 material properties hidden within these equations. I'm going to show you a challenge. It's a very fun experiment you can try. And I've sent a video to Jaya, so please Jaya, forward that video to the students. It's an experiment I have tried. Non big magnet would is not attracted by a magnet, or should not be attracted by a magnet. But if I put if I put paper on a piece on water and I bring magnet to it, you will see that the paper is apparently being attracted to the magnet. That's an experiment. There's a video I did. I am sending. Yeah, please share it with. I want you to see why that is happening. So, now is the magnetic material property mu R. Let's see who can come up with the answer. First of all, to that video. So now, if you look at this equation now, we have 4 field terms, C, E, B, H, but 2 of those terms, D and E, are related to each other, D and H are related to each other. Only a mathematical term we have, so that our Gauss law becomes material independent. H was purely a magnetic field term, the mathematical term we had developed, so that my del cross H is equal to J, the Ampere's law part becomes equal to my, becomes material independent. I don't have to worry about what material I am in. And then E are related by the material by a term called for the permittivity, and B and H are related by a term called mu, which we call magnetic permeability. Hidden within these equations are also 2 sources. You have rho, which is your charge density, and is, of course, for field, and you have J for your T, and for the field, for the magnetic field. There are 4 field terms, 2 material properties, and 2 sources which are present in in these Maxwell's equations. What we have written, Maxwell's equations we have written here are called the differential form or also called the point form. They are true at any point in the specific space. That's what these Maxwell's equations are written in that form. Henceforth, when we start doing waves, it's the point form which you start using rather than the integral form we had looked at before. Integral form is really good at looking at how the fields are varying in space from sources, but once you have know what the fields are doing, what the fields are going to be doing with time, then the point form becomes really, really important, really, really useful. Let's consider these equations and let's see why Maxwell revolutionized our field. In fact, the complete field of electronics engineering started from these Maxwell's equations. And sorry, just a second. Too low for me to take it out. All right. So let's consider this equation again. I have del dot E is equal to rho. Del dot V is equal to 0. I have del cross H is J plus del D by del T. I have del cross E equal to minus del V by del T. And if you consider these 2 equations here, there is something interesting which you can pick up very, very quickly. You notice, if my B field changes with time, if B field is varying with time, if B field is not varying with time, if B field is constant, that's a static, that's a magnetic. But if B field is varying with time, then I would create an electric field. And that electric field would curl around perpendicular to B field. And normally, if B field is varying with time, electric field would vary in space, curling around that B field, but most probably it would also vary with time. If electric field is varying with time, then this would get into del D by del T. That is nothing but del by del T of epsilon E, which means that this would create a magnetic field H which would curl around E, which means that this would get coupled into this part over here too. So if you look at these equations, these are 2 first order coupled partial differential equations. And not only they are but you notice is between space and time variation creates an electric field in space. Del cross is a spatial variation. Creates an electric field in space which probably is varying with time, which creates a magnetic field in space which gets coupled back in there too. So there's an oscillator in time here and an oscillator in space. Going back to your first year, if I asked you, how are waves created? Show me a simple experiment with which you can create waves. One simple experiment you can easily do is, let's say you have a mass and a spring, mass and a spring connected all together. If I move one of these masses down, what would happen? This mass will start to oscillate around this region, but the energy will start to travel forward too. So there is an oscillator in space here, which is allowing this mass to move around in its local position, but there is also an oscillator in time, which is the coupling which I have created. I move the mass on one place, that energy is pushed, there is a spring connected, that spring gets stretched, part of that energy gets moved to the next mass, and thus each of those masses start to oscillate different times. That's how the waves would be. For waves to be created, there has to be always an oscillator in time and an oscillator in space. There always has to be an oscillator in space for a wave to be created. Wave is propagation of energy without propagation of the matter through it. And if you look at these particles, you see that same kind of coupling happening in these two equations. You have a time variation in B creating a spatial variation in E, which starts to create, it starts to get coupled into the first equation up here, which creates a spatial variation in H, which gets coupled back, and thus I have two first order coupled equations, and they are coupled in time and space. And from this, you know that the result of these two equations should be a wave. And this is the exciting. If you notice, all the equations we have derived have come from either very simple time-varying fields, time-varying experiment, which is del V by del T, that come from electrostatics and magnetostatics. There is no time variation at all. They are coming from the fact of how charges and current affect the forces around them. That's how this whole equation has been derived. As soon as you add del D by del T in there, if this del D by del T is not there, then there is no coupling happening. But as soon as you add del D by del T, the displacement current is one of these in the Ampere's law. As soon as you add, the two equations become coupled and the solution should be a wave. And think about it, this was one of the major unifications that happened. This was unification of charges and currents with light. Light, which was considered to be a wave, could now be explained by the same material properties we are using to explain how the forces are going to happen, how the charges are going to create forces between them, how the currents are going to create forces between them. This was a historical time in physics. If you remember from your first year mechanics, your first unification was the unification of Kepler's laws with Newtonian physics. Newton said force creates mass times acceleration. Kepler, through his experiments, through his thought process, initially he was totally wrong, and then as he kept on doing more and more calculations, he finally realized that you could explain how the galaxies are formed, how the Earth is rotating about the Sun by the same equations you're using to describe how ball is rolling on the ground. How if I push you, you will have you will fall over, or you will have an acceleration. By those very same equations, I could describe the various things. Second major unification which happened in physics was this one over here. So far, everything you have done so far was defined based on how forces are created in materials. How if I have a charge, they will start to attract with each other. How if I have a current, they create forces between two current carrying wires, so there must be a field. We define those forces through fields, so there must be a field. And depending on the material properties, depending on whether it is a strongly magnetizing material, UR is much, much larger, or whether it's a weakly magnetizing material, the forces would be different. But as soon as out comes light, out comes the wave. For the second half of the course, now we are going to understand how these waves are created from these equations, the second part of the unification. We have understood how electric fields and magnetic fields lie within materials, how they create forces, how they allow charges to move around in Faraday's law, for example. Now we are going to understand how they can create waves. The second part of the unification is happening here. I think it would be good time to talk, but before I do that, we would be using this curl product a lot. So let me make sure that you understand the curl product. So let me just summarize that. If I have a vector, let's say this vector is in x direction, y in y direction, plus az in z direction, then the curl of vector A is going to be given by, say, to represent it is the matrix form, x, y, z. You have the derivatives, partial derivatives in each direction, and you have the components in each direction. The del cross A is going to be given by, I go x, when I go to this, I go to the next column, I multiply cross terms, and this term is added, this term would be plus, the next column is. So it would be del Az by del y minus del Ay by del z. That would be what is in the x side. If I go to the y column, now I'm in this column over here, I walk to the next column to it. Again, remember, I always want to go counterclockwise. So I go to y, go to the next column, I multiply del by del z of this, multiplied by ax. I would get del ax by del z minus, I multiply this term with the term over here. So I get del Az by del x. And finally, I go to the z column. Again, I walk counterclockwise. I have the x column here. So I multiply this with this, and this with this, and do the right subtraction. So I get del Ay by del x minus del Ax by del y. Remember, the result of del cross A would be in a plane perpendicular to vector A. Keep this in mind as we do the waves, as we start developing it up. We would be using this cross product a lot. Would be using curl a lot, at least in XYZ components, in the Cartesian components. I'll stop the lecture here for today. What we will do tomorrow is initially, for about 20 to 30 minutes, I'll just talk about waves in general. What is a wave? How can you represent it mathematically? What should be wave a solution of? I know when I get a mathematical equation that the wave is going to be a result. So I'll spend about 30 minutes roughly talking about waves in general, and then we will start looking at how Maxwell's equations leads to electromagnetic waves. And we'll come up with certain solutions in certain cases for that. Jeff, do you have any questions? I will get a headset tomorrow, so we should have much better audio tomorrow onwards. I'll get a specific headset.
Sure. We expect audience
Right.
analytics.
Do you have any questions?
Yes, sir.
Or do you have any questions?
No, sir. So we expect a good audio tomorrow, sir. Otherwise, everything is good.
Sorry? Can you speak?
The audience around slightly it is disturbing. Otherwise, everything is good, sir. The video is all everything is good.
All right. So what I will do is I'll get the headsets tomorrow for the audio. Even your audio is like little bit. So I think hopefully tomorrow it should be okay. Can you come up about 10 minutes earlier than the class so we can make sure that the audio is okay tomorrow?
Sir, minutes earlier. 10 minutes earlier. Yes, I have started by 8:45 today. I have